The objective of this video is to give you an introduction to balancing chemical equations and to practice balancing some simple equations. Now, I want you to see chemistry as a language. And in this language, all the letters and numbers that you use are given in the periodic table. By now, you know how to write the formula of compounds, ionic compounds, or covalent compounds. For example, if I take simple ionic compounds like sodium chloride, sodium you can find in group 1. So by now, you know group 1 elements make +1 charge, and if we think about chlorine, it's in group 7, and group 7 elements make -1 charge. And when these elements come together, there is charge neutrality. So in order to achieve charge neutrality, these atoms combine in a suitable ratio and gives you the formula. For example, if we take another couple, for example, magnesium. Magnesium is in group 2, so it makes 2+ charge. And if you take something like nitrogen, nitrogen is in group 5. Things in group 5 make 3- charge. So in order to achieve charge neutrality, you can do this kind of an exchange. So you will end up with a formula like Mg3N2. Now these subscripts you see in a formula are an identity of that formula or the compound. In the event you don't see a subscript, you will always assume that there is number 1, or only that we just don't show 1 in the subscript, so you will not see it. So all the other numbers we show it, and this subscript is a part of the formula. So when it comes for the part of balancing equation, we never change these subscript. So writing this formula is like using this language to write words, and writing chemical equations is like writing sentences using these words. In these sentences, we have two basic components: reactants on the left side of the equation and products on the right side of the equation. And then we use an arrow to show the direction how reactant goes into product. Is this reaction occurring from left to right or right to left? The direction is shown by the arrow. Usually we draw the arrow from left to right, from reactant to product. And when we come to balance chemical equations, we consider the concept of conservation of matter, meaning that if this reaction takes place in a closed system, if nothing is moving out or nothing is moving in, the number of atoms you have on the reactant side should be the same number on the product side. If you have only one calcium atom on the reactant side, you should have only one calcium atom on the product side. If you started with one calcium atom, you can never end up with 2 calcium atoms on product side. If you find 2 calcium atoms on product side, that means you had 2 calcium atoms in reactant side. So the numbers of each atoms from each element should be balanced. So the whole concept of balancing chemical equation is based on the concept of conservation of matter. Now, when we have a balanced chemical equation, you can find each element on both sides will have the exact same number of atoms. In here, you will have 2 multiplied by 2, a total of 4 hydrogen atoms on reactant side. And now you can find 2 multiplied by 2, 4 hydrogen atoms on the product side. So all types and the numbers of atoms are going to be same on the both sides. And once you have the equation properly balanced, you will have the smallest whole number ratio. So what is this whole number ratio? These are actually the coefficients that we are looking at. I mentioned that we are not going to touch the subscript. Subscript is an identity of that formula. Never touch the subscript. We only change the coefficient. In the event you don't see a coefficient, that signifies you have 1 as your coefficient. Only that when we have 1, we just don't show it. So what this coefficient shows you is actually a ratio. A ratio, how these reactants are related to each other and how reactants are related to the products. For example, according to this balanced equation, 2 molecules of hydrogen will react with 1 molecule of oxygen to give 2 molecules of water. We can use the same simple whole number ratio in different magnitudes, like bigger numbers. But if you really look into them, you can simplify all these big numbers into this same simple whole number ratio. So in the balanced chemical equation, what you find is the smallest whole number ratio. Let's look at few simple examples and see how we can balance them. Now in this equation, when you examine the reactant side and the product side, you can see on the reactant side you have only 1 iron atom, but on the product side you have 2 iron atoms. So first, examine the equation and identify number and type of each atoms on both sides. And you are only adding coefficients to balance the equation. Only the coefficients. Do not touch the subscript. Never touch the subscript. The only thing we change is the coefficient. Now let's list down the elements we have on both sides. We have iron on reactant side and then iron on the product side. We have oxygen on reactant side and oxygen on product side. We have 1 iron atom. On this side we have 2. Over here we have 2 oxygen atoms. Here you have 3 oxygen atoms. Now according to conservation of matter, the number of oxygen atoms on both sides should be the same. The number of iron atoms on both sides should be the same. Now, one easy way to start with is compare the most complex molecule with the others. You see 2 iron atoms here, but only 1. So let's change what? The only thing we change is the coefficient. Never touch subscript. Now when we put the coefficient here, it signifies that you have 1 over here. You just don't do anything with it. If you have 1, you don't even show it. So 2 multiplied into 1. Now you end up with this change. You end up with 2 iron atoms. Now it seems like the ions are balanced. How about oxygens? Over here you have 2 and here it's 3. Think about the smallest common number that can be divided by 2 and 3. That would be 6. So what if we can have 6 oxygen atoms on both sides? If you want to have 6 oxygen atoms, never touch this. What you put is the coefficient. What will give you 6 if you have a 3? Divide 6 by 3 is 2. So 2 multiplied by 3, you get 6. And now you need to get 6 oxygen atoms on the reactant side. 6 divided by 2, you have 3. Troubleshoot it. 3 multiplied by 2, you get 6. Then oxygen atoms are balanced, but adding these 2 over here, what happened to the number of iron atoms now? You have 2 multiplied by 2. Now you're ending up with 4 iron atoms. If you are going to have 4 iron atoms on the product side, that means you should have 4 iron atoms on reactant side. That means you have to get rid of these 2 and put the coefficient 4. Now you have all the numbers balanced. You have 4 iron on reactant, 4 iron on product. You have 6 oxygen on reactant and 6 oxygens on product. Now this equation is balanced. Let's take another equation. Sort out the elements in both sides. You have 2 aluminums on reactants, but 1 aluminum on product. You have 3 oxygen on reactant, but only 1 oxygen on product. You have 1 carbon on reactant and 1 carbon on product. How about chlorine? You have 2 chlorine on reactants, but 3 chlorines on product. Now let's look at the most complex molecule. It's more like Al2O3 or AlCl3. Compare these. You have 2 aluminum, 1. So we will put 2 aluminums on this side by putting the coefficient 2. By putting this 2, now we are altering the total number of chlorine. 2 multiplied by 3, that is 6 chlorines. If you are going to have 6 chlorines on this side, you should have 6 chlorines on this side too. How do you get 6 chlorine? Put the coefficient 3. 3 multiplied by 2, you get 6. Now that part is solved. Now let's see what else is remaining. You have oxygen, how many? 3, but on this side you have only 1. So let's change the number. If you want to make 3 oxygens here, then you have to put the coefficient 3. Now you managed to change the number of oxygens, but what did it do to the number of carbons? Now 3 multiplied by 1 is going to be 3 carbons now. If you have 3 carbons on this end, you should have 3 carbons over here. And if you want to get 3 carbons, you will have to put the coefficient 3 into 1, that is 3. Now compare the total number of elements in both sides. Aluminum balanced, oxygen balanced, carbon balanced, and chlorine balanced. Now this equation is properly balanced with the simplest whole number ratios. Another example. You have magnesium. You don't see a coefficient here. You don't see a coefficient in the subscript. And even in this one, you don't see any coefficient in front. And check out the numbers in both sides. How many you have? You have 1 magnesium, and what you have is 1 into 2, 2 nitrogens. Now what you have here, magnesium, you have 3 of them, and nitrogen, you have 2. Try to balance it. If you have 3 on this side, then you must have 3 on the other side. Put a 3. Is it balanced? Yes. Now the equation is balanced. Everything in both sides are balanced. Another example. You have hydrogen, nitrogen combining to make ammonia. Sort out the elements. Reactant side, you have hydrogen, and product side, how many atoms you have. Reactants, you have 2 hydrogens. Products, you have 3 hydrogens. Reactant, you have 2 nitrogen. Product, you have 1 nitrogen. Try to balance the numbers. Think about common numbers. Now this one seems much more easier to start with. You have 2 nitrogen on reactant and 1 nitrogen on the product. So let's bring it to 2. If you're turning it to a 2, then you need to put the coefficient 2. When you put that coefficient 2, what happens is 2 multiplied by 3, this hydrogen turns into a 6. You need to have 6 hydrogen on the reactant side as well. If you want to have 6, what should your coefficient be? It should be 3 hydrogens. Now check if you have the same number of atoms for each element on both sides. 3 into 2, you have 6 on reactants. 2 into 3, you have 6 hydrogens. 1 into 2, you have 2 nitrogens on reactants. And 2 into 1, you have 2 nitrogens in products. Now this equation is balanced.